In this lecture, we will talk about heat transfer in extended surfaces. The boundary value problems we have seen so far have been first-order BVP. Here, you will learn how to solve second-order boundary value problems, which often result from heat transfer in extended surfaces. At the end of the lecture, you will know how to derive a heat balance for extended surfaces, simplify the system and understand its significance, and convert a boundary value problem for an ordinary differential equation into a system of algebraic equations using the finite difference method. First of all, what is an extended surface? When you have a plane wall in contact with a fluid, the amount of heat transfer is obviously limited by the surface area. If you want to transfer a lot of heat, then you can do this in three ways. 1. Increase the temperature difference. 2. Increase the heat transfer coefficient. Or 3. Increase the surface area. Often, it is not possible to do 1 or 2. The duty of a heat exchanger is generally fixed by design, so you cannot really change the temperatures. The heat transfer coefficient depends on flow conditions, and these may also be fixed for a given design. That just leaves the surface area. Rather than just making the surface bigger, an efficient way to increase heat transfer is to add extra surface to the walls. This can be done by adding fins, louvers, and other shapes to the surface. A plate fin heat exchanger, for example, has extra fins between the plates to increase the surface area significantly. Air coolers have fins on the outside of the tubes to increase the surface area in contact with the air. Outside the industrial setting, most people will have seen fins on their radiators at home. To understand and calculate the benefit of adding fins to a plane wall, we can derive a model to determine the temperature profile in the fin and ultimately the amount of heat transferred to the surrounding fluid. Let's first consider a rectangular fin connected to a wall held at 85 degrees Celsius and surrounded by air at 15 degrees Celsius. The dimensions of the fin are shown here. The length is L, width is W, and the height is 2b. If you're wondering why there is a 2 here, it is because it makes the equation slightly simpler later on. Although it is not shown in the drawing, here we assume that B is much smaller than L. First, we need to decide how much detail to include in the model. We can make a number of simplifying assumptions. Although the temperature T depends on X, Y, and Z, we can often just consider one of the dimensions. Since B is much smaller than L, we can expect that the temperature is not that much different in the Y direction. We will assume that T is a function of Z only. Since the largest surfaces are the top and the bottom ones, we can neglect the small amount of surface on the sides of the fin. The heat transfer coefficient depends on the conditions of the surrounding air. To simplify the model, we can take this to be a constant. In the real system, the air between the fins is likely to heat up, and we will need to account for the flow of air taking heat away from the fins. A good simplification is to assume that the air is at uniform temperature, unaffected by the heat coming from the fins. It is an infinite sink for the heat. Now we can derive a model using those assumptions. All variables depend on Z. There is heat conduction in the Z direction and heat flow by convection out of the fin. Our control volume is a differential element with uniform cross-section. Start as usual by writing the general energy balance equation. Accumulation term equal to the sum of all heat flows going into the control volume minus the sum of all heat flows going out of the control volume plus the generation term. Now we apply assumptions and details of the system. It is at steady state, so no accumulation term. No generation term because it's just a metal fin. Now define the inflows and outflows. QZ for in and QZ plus delta Z for out. Then there is also the convective transfer from the fin to the air, which we will call QConv. And then write these heat flows as fluxes, which we know how to formulate in terms of the temperature T and areas perpendicular to the flow. That is, the heat flow, capital QZ, is equal to the heat flux, small qz, times AC. And QConv is equal to H times AS times the difference between the temperature and the temperature of the air. What are AC and AS in this case? AC is easy. It is the cross-section of the fin, which is 2B times W. AS is the blue shaded area shown on the top of the fin. It is W times delta Z. But remember, there is an equal area on the bottom from which the heat is transferred. So the overall area, AS, is 2W times delta Z. We are neglecting the areas on the sides. In other words, we are also assuming that B is so much smaller than W, so that the heat transfer from the edges won't contribute much. We can now substitute the expressions for the areas AC and AS into the energy balance. As usual, we rearrange and take the limit as delta Z tends to 0, giving us a differential equation. Lastly, we apply the Fourier's law, which is heat flux, small q, is equal to negative K times the change in the temperature with respect to Z. And we have the final differential equation, assuming K is independent of temperature. The last thing we need to do is consider the boundary conditions. We said already that the wall temperature is held constant at 85 degrees Celsius. The other boundary condition at the other end states that the heat flux from this end is 0. This is a reasonable assumption because B is much smaller than W. Nearly all of the heat loss will be from the main surface at the top and bottom of the fin. By comparison, the losses from the edges are practically 0. So that is our model. And next, we will want to solve it. In this case, we can solve it analytically. To make it easier to solve, we can define a new variable and parameter. T prime is equal to T minus T air, and alpha squared is equal to H divided by KB. You can use this to write the equation in a very simple form. The second derivative of T prime is equal to alpha squared times T prime. We know how to solve this equation. What function, when differentiated, is itself, but multiplied by a constant? It's e raised to a constant times x. And therefore, the second derivative is that constant squared multiplied by that function, which is what we have. Therefore, the general solution is T prime is equal to C1 times the exponential of alpha z plus C2 times the exponential of negative alpha z. We have two possible solutions because negative alpha squared is alpha squared, so they both satisfy the equation. Now, it's just algebra. First, we can substitute back for t, and then apply the two boundary conditions in order to get the two constants, C1 and C2. You need to solve these boundary conditions simultaneously in order to get C1 and C2. And that then gives us C1 and C2 as follows. And the final solution is here. You can then plot this to see how the temperature profile looks for different values of H over Kb and L. Here, I kept H over Kb fixed and increased L. The larger the L is, the more heat is lost by the fin, and the colder its temperature becomes. Let's do it on paper so you know how it's done step by step. So our energy balance is accumulation is equal to in minus out plus the generation term. The accumulation term is equal to rho v Cv dt dz. We can write the inflows of heat as the summation of all incoming heat flows, Q in, and the heat outflows as the summation of all of the outgoing heat flows, Q out, plus the generation term. Okay, so now we can apply some assumptions and put in some of the details. So we know that Qz, so the heat flow that is equal to the heat flux, small q, at z, times the cross-sectional area. So this area here. Okay, so this is due to conduction. Capital Q is due to conduction, QZ. So the area we want is this one, the cross-sectional area of the fin. So that's 2B times W. But now let's denote that as AC. Okay, so AC is equal to 2B times W. Okay, and then we also have heat loss due to convection. So we can write that as Q conv. And this is equal to the heat transfer coefficient H times AS times the temperature minus the temperature of the air. Okay, and AS, okay, so that area is this area. So this is our control volume. Okay, and when we talk about convection, so the area perpendicular to the heat flow due to convection is this. Okay, so that is the width W times delta Z. Okay, but we have two because we have one at the bottom of this. Okay, so we have two surfaces, one at the top and one at the bottom. So we have 2 times W times the thickness of our control volume, delta Z. Okay, so now we can substitute in these expressions into our balance. Okay, so we can drop the accumulation term because we assumed it's steady state. So 0. So Q in. So we only have QZ. Okay, and QZ is equal to heat flux at Z times AC. So we can write QZ and AC is 2B W. Okay, so minus Q out. So Q out is this, QZ plus delta Z. Okay, so we have, so let's write that in terms of the heat flux as well. So that's QZ plus DZ. Okay, so the heat coming out of our control volume due to conduction. So times AC. So that's times 2BW. And then we also have heat loss due to convection. Okay, and this is that. So we'll have minus H. Okay, so AS is 2W delta Z T minus the air. Okay, so now we can divide each term by 1 over 2B W delta Z. So now you can see why we defined the height of our fin to be 2B. Okay, because we have all of these terms for the area. There is a 2 in each term. So they will cancel out. So it makes the equation simpler. Okay, so let's evaluate this. So we'll have 0 is equal to QZ. Okay, so this will disappear. And then minus QZ plus delta Z. This will disappear as well. But we'll have delta Z in the denominator. Okay, so what about this term? So we'll have minus H. Okay, so the 2W and delta Z will cancel out with the 2W delta Z here, but we'll have B in the denominator. Okay, and we have T minus the air. Okay, so now we can take the limit as delta Z tends to 0. So we can write this as 0 equal to negative D Q dz. Okay, so just the definition of derivative minus H over b t minus t air. Okay, so now we know that the flux depends on the temperature. So we need to express this in terms of temperature. And this is due to conduction. And we know that we can use the Fourier's law to express the flux in terms of the change in temperature. Okay? So by Fourier's law, this is equal to Q is equal to negative K dt dz. Okay, so let's substitute that into our differential equation. So we'll have 0 is equal to negative d dz of negative k dt dz minus h over b times t minus t air. And then we can evaluate this. So this will become k. So assuming k is independent of temperature. So second derivative of t with respect to z minus h over b t minus t air. Okay, so we can also write this as the second derivative of t with respect to z minus h divided by b k, okay, t minus t air. This is equal to 0. Okay, so we can write this in a more compact form if we define t prime to be t minus t air and define this group of constants here as alpha squared. Okay, so that's h bk. Okay, so using this transformation, let us see what will be the form of our differential equation. Okay, so here we have second derivative of t. Okay, so let's take the derivative of this. So first derivative of t prime with respect to z is dt dz. And then second derivative of t prime is just the second derivative of t with respect to z. Therefore, we can write our differential equation as the second derivative of t prime, okay, with respect to z. This is just equal to alpha squared okay, so we have t minus t air, but that is just t prime. Okay, so I shouldn't have put this inside the bracket, so let me rewrite that. So this is our differential equation. Okay, so I'm sure you can recognize this. So there is a known solution to this differential equation. So what it says is that the second derivative of a function t is equal to itself times square of a constant. Okay, so we know that, okay, so the function, so if I have a function, an exponential function, so let's say f of x is equal to e to the ax. Okay, so the first derivative of that with respect to x is just, okay, the function e to the ax times a. Okay, and then if you take the second derivative, okay, so this is just the function again. This time you have constant squared. Okay, and this is exactly what we have here. So the second derivative of a function is the function itself times square of a constant. So therefore, the solution to this, so t prime, so this is equal to c1 e to the alpha times z, so exponential of alpha z. Okay, so that plus c2. Okay, so exponential of negative alpha z. Okay, so you'll see that this part here is a solution of this, and so is this one. So if you take the second derivative of this with respect to z, you will see that this satisfies this equation. So now let's write this T prime in terms of our temperature. So we defined earlier, okay, that T prime is equal to T minus T air. So this is T minus T air is equal to C1 exponential of alpha z plus C2 exponential of negative alpha z. So now let's apply our boundary conditions to solve C1 and C2. So our first boundary condition is at z equal to 0. So the temperature at the wall, let's apply this to our solution. Okay, so T at z equal to 0 is TW minus T air equal to, okay, so this is at z equal to 0. Okay, so at z equal to 0, the exponential terms will become 1 because we will have exponential of 0. So we will only have C1 plus C2 here. Okay, so using our second boundary condition. So our second boundary condition says that, okay, so at the end of our fin at z equal to L, the flux is 0. So writing that mathematically, so at z equal to L, the flux is 0. So the change in temperature with respect to z, okay, this is at L, at the end of our fin, this is equal to 0. Okay, so in order to apply this, let's take the first derivative of our solution. Okay, so the first derivative is dt prime dz. Okay, so taking the derivative of this is C1 alpha exponential of alpha z plus C2. Okay, so we have negative alpha e to the negative alpha z. Okay, and then evaluate this at z equal to L. So we know that this is also equal to dt over dz. Okay, so at z equal to L, we know that this is 0. So we have 0 equal to, okay, so we have C1 alpha e to the alpha L, because now z is equal to L. Okay, so we have a negative sign here. So minus C2 alpha e to the negative alpha L. Okay, so now we need to solve the two equations simultaneously. So this one and this one to solve for C1 and C2. Let's rearrange this first. So from this one, we can solve for C1. So C1 is equal to C2. Okay, so alpha e to the negative alpha L divided by, so alpha e to the alpha L. Alpha will cancel out, and I can write C1 as C2 e. Okay, so this will become negative 2 alpha L. Okay, so if we put this in the numerator, then we'll have a negative sign, and we can just add the exponents. So we have this negative 2 alpha L here. So this is C1. So we can substitute this into this one to solve for C2. Okay, so substituting it in here, we'll have TW minus T air is equal to C1, which is this C2 e to the negative 2 alpha L. Okay, so that's our C1 plus C2. So Therefore, TW minus T air. So we can factor out C2 and we'll have 1 plus exponential of negative 2 alpha L. Okay, so therefore C2 is TW minus T air 1 plus exponential of 2 alpha L. Okay, so I can multiply the numerator and the denominator by e to the alpha L. And this will become, okay, temperature of the wall minus temperature of the air, E alpha L. And then we can distribute it here in the denominator. So multiply each term by this. So we'll have E alpha L. Okay, so I have negative 2 here and I have positive 1 here. So we'll have, okay, so plus E to the negative alpha L. Okay, and then I can write this in terms of the hyperbolic functions. So if you can remember, cos x is equal to e to the x plus e to the minus x over 2. So therefore, e to the x plus e to the minus x is just 2 cos x. So C2 is equal to TW minus T air E alpha L, and the denominator is just 2 cos alpha L. So now let's use this to get C1. Okay, so C1 is equal to this, C2 times the exponential of negative 2 alpha L. So C2 is this. Okay, times E negative 2 alpha L. Okay, so therefore C1 is just TW minus T air. Okay, so I have plus 1 here and negative 2 here. So this will become e to the negative alpha L. And we have 2 cos alpha L in the denominator. Okay, so now that we have C1 and C2, okay, so C1 and C2, we can now write our solution, okay, using the expressions that we derived for C1 and C2. So we'll have T minus T air. This is equal to C1, but C1 is just this. So we have TW minus T air exponential of negative alpha L over 2 cos alpha L. Okay, and this is multiplied by E to alpha Z. Okay, this one, C1 times E to the alpha Z. And then we also have this one, C2 times E to the negative alpha Z. So let's write that. So C2, okay, so C2 is this, so plus C2. So TW minus T air E to the alpha L 2 cos alpha L, and this is times e to the negative alpha Z. Okay, so we can tidy this up. So we'll have T minus T air. So we can factor out T, W, T air, and 2 cos alpha L because they both appear in both terms. Okay, and then we have bracket exponential of E alpha L E alpha Z plus E alpha L E negative alpha Z. So therefore, we can write T, T air, TW minus T air. This is equal to E alpha L, E alpha Z plus E alpha L, E alpha Z divided by 2 quash alpha L. So this is our solution. So when you substitute in alpha into here, then this will become exactly like the expression that we have on the slide. Again, this is the exact solution that we derived analytically. I will stop here now, and in the next part of this lecture, I will show you how to solve the second order differential equation numerically using a finite difference method, which involves transforming the second order ordinary differential equation into a series of algebraic equations, which can then be implemented and solved in MATLAB using a matrix representation.